So I'm starting recording for this presentation. So it's a pleasure to have Yuning Lee with us. So he's from York University, and we'll be talking about estimating time-varying networks for high-dimensional time series. Again, Yuning, you have 20 minutes, including the question. Thank you.
Thank you. Thank you for the organizing and providing me this opportunity to present this work. So this is a joint work with Jiachen Degui Li from University of York and Oliver Linton from Cambridge University. And today I'm going to share with you how to estimate the time-varying networks for high-dimensional time series. So network models are not very popular, and it's an efficient tool for exploring interconnection within a set. So if it's a set of people, then it's the social network. If it's a set of neurons, then we have the neural network. So in this paper, we focus on a set of time series variables. So what is a network? A network is a mathematical definition of actually has two components. V is a set of vertices. So in our paper, it represents a set of variables, and the E is a set of edges that represents the linkages between these variables. So a simple example here is we have 4 variables, and we can use the covariance matrix to define the link between each variables. For example, if variable A and variable D has non-zero covariance, then we draw a link between them. And this is just a simple example. And in this paper, we don't use covariance to define this matrix, to define this network, but use some other matrix to define a network, and we will see it later on. So in the literature, most of the paper just studies a static network, and there are some steps to relax this assumption. For example, to introduce the abrupt structure break or smooth structure break. But this paper I mentioned here just assume the data set are independent, which are often violated in practice. So to consider the serial dependence, we use a VAR model. So this is a fundamental modeling tool for time series data. Here, xt is our observation vectors at time t. A is the transition matrix. Sigma is the covariance matrix of the errors. And epsilon t is a sequence of IID random vectors with mean zero and identity covariance matrix. So we also consider a high-dimensional VAR model, which means the number of variables here can be much larger than the sample size. And in such a case, we usually need to introduce some structure for the VAR model to reduce the number of parameters. Then we can do the estimation. So here are some examples, but this paper just assumed the stationarity of the time series. And in our paper, we want to consider the time-varying structure of the model. Therefore, in this paper, we consider a high-dimensional time-varying VAR model and to explore the two network structure from this model. And we propose a 3-step estimation procedure to estimate the network, derive the asymptotic properties, assess the performance through simulation studies, and finally apply this model to the Fred MD micro data set. So this is also the structure of my presentation. So next I'm going to show the model framework. So this is the model we use in our paper. A little different from the equation I showed in the previous slide is that now there's a subscript T here for the transition matrix, which means this matrix will evolving over time. And also for the covariance matrix, it has a script T. So that means the volatility matrix will also change over time. And here I denote omega T the inverse of the covariance matrix. So it's also called the precision matrix. And under this assumption, it will change over time as well. Then we try to define two networks based on this model. So we follow the Bargozzi's and Brownlee's paper to define two networks. One is the Granger causality network, and the other is the partial correlation network. So first of all, to define the Granger causality, we know the Granger causality is try to investigate the causality between two variables. So for example, if we have D variables here, we say variable J Granger causes variable I if the lag of variable J can be used to predict variable I given the other variables. So in the context of stable var model, this information are all saved in this matrix, this transition matrix. So it means if the AKIJ, this entry is not equal to 0, then variable J Granger causes variable I. So with this matrix, we can define a Granger causality network. And this is the formula how to define this linkage or edges for the network. So just to say AKIJ is not equal to 0, then we have a link between variable I and variable J. And this is a directed link because AKIJ is not equal to AKJI. So similarly, we define the network called the partial correlation network. So the partial correlation is a correlation for two variables given the others. And we know from Dempster's paper that the partial correlation has a 1-to-1 mapping with the precision matrix. So we can define this network using the precision matrix. So if the IJ entry of the precision matrix is not equal to 0, then we will have an edge in this network between variable I and variable J. So these two slides just define the network for a static var model. And in our paper, we need to consider the network for the time-varying var model. So firstly, if we only consider a specific time t, then we can easily define the local network. And it can be estimated just using the local samples. And we don't even need to use a time-varying var model. So in this paper, we consider two more interesting networks, which are the uniform Granger network and the uniform partial correlation network. So the uniform Granger network is a Granger network that is defined by some time t, such that AKIJ at time t is not equal to 0. So that means this network captured whether one variable Granger causes the other at some period of time, maybe not the whole sampling period. And similarly, we have the uniform partial correlation network. So if for some time t, this precision matrix is not equal to the entry of this precision matrix is not equal to 0, then we have the link between these two variables. So these two networks are what we want to estimate. So let me show you how we do the estimation. So for notation simplicity, we consider only var1 model, and we write it like this. And the strategy for estimation is we estimate it row by row. So if we take out the ith row of this model, we can have such an equation. And this is just a regression equation, but note that we have a lot of variables here, which will even larger than the number of variables will even larger than the number of observations. And also the parameter here will change over time. So to deal with these two problems, we firstly use non-parametric estimation, the local linear smoothing, to use kernels as weights to estimate this the parameter locally. And then to deal with the high dimensional problem, we use lasso type of estimation. So we combine these two in our estimation. And even though that is not enough to estimate the network, we only estimate the parameters. So the whole process estimation procedure is like this. So just ignore the step 0. We can do factor adjustment, which means we can first estimate a factor structure on this data set, and then estimate this var model on the idiosyncratic component. Then let me start with the first step. That's what I just mentioned. We estimate a time-varying lasso. We use time-varying lasso to estimate parameter. And then in the second step, we use the estimates from the first step to re-estimate the parameters. And then in the step, we can use the estimates from the second step to construct the estimates for the network. So why we need the second step, that is mainly because the lasso type estimators cannot achieve the property called the oracle. So that means true zeros are not estimated to be non-zeros. That's why we need a second step. So I'm not going to the details of these things. And then we estimate the partial correlation network. So in the first step, we estimate the errors of the var model, and then use this ET hat. We first estimate the sample covariance matrix locally using some weights, and then use this time-varying Klein method to calculate its inverse. So we get the precision matrix. And using these estimates, we can then define our estimates for the network, the partial correlation network. So this is how we estimate the two networks. And in the paper, we not only derive the consistency of these estimates for the parameters, and the main theory are these two. So we provide the consistency of the estimators for the two network. Then let me show some result of the real data analysis. So we applied our method to the Fred monthly data set, and that include 127 US microvariables, and they are classified into 8 categories. And the first step, we distracting common factors using a factor model, either with constant factor loadings or time-varying factor loadings. So finally, we decide to use the time-varying factor loading factor models because it can use less number of factors but explain more variance of the data set. Now, in this two figures, I shows you the
around I would say 4 minutes, 5.
Yeah, thank you.
Okay, thank you.
So in this figure, I shows you so the left one is what happened if we only estimate a static var model, and in the right figure, I shows you the result of our model. We estimate a time-varying var model. So we can see in the left figure, there's less number of links between the nodes. So one of the reasons might be if the parameter is sometimes positive and sometimes negative, then if we estimate a static model, then it could be estimated as 0. So we cannot find the link between these two variables. But if we estimate a time-varying var model, then the parameter will be sometimes positive and sometimes negative, and we just find out this Granger causality. And then in this slide, I compared also two network. The first one is what if we don't detract the factor structure from our data set. And the second figure is again the result of our model, but with the factor adjustment. So now we can say if we don't do the factor adjustment, then the network will be much denser. And sometimes in the literature, the common factors for this data set is interpreted as business cycles. So this Granger causality between these micro variables are mainly caused by this business cycle components, which are much persistent, or in other words, these factors has very high autocorrelation. But if we distract these factors, this micro variable just have little predictability between each other. Then in this figure, I shows you there is some time varying pattern in these parameters, and I'm not going to show the details. And then here I shows you the partial correlation network we estimated from the data set, and it's just like this. And we again can look into some parameters, how it changes over time. So again, we can see some time varying patterns for this entries of the precision matrix. So we believe that in this data set, using a time varying VAR model is much better than using a static VAR model. Okay, so here's the summary. We develop a estimation method for the networks for the high dimensional time varying VAR model, and derive asymptotic properties and apply them in the Fred data set. So thank you.
Thank you very much, Yuning, and thanks a lot for the great talk and also for finishing on time. So we have a few seconds for question, otherwise I can ask one. Okay, there's no question. Right, so
I have a small question, sorry.
yeah, please.
Just for the theory to work, I don't know if I missed this detail, but do you require some specific tail condition for the noise, or number of moments to get your asymptotic or non-asymptotic results?
Sorry, you want to know about the theory part? Or
Yeah. I was wondering about the assumption that you have on the noise.
Okay. Let me show
of the VAR process.
So the first of all, our model is non-stationary, but we need to assume it's local stationary. So for each time t, and the parameter should be make sure this model is stationary. And then we also have the exponential tail condition for the variables.
Okay, so do you assume sub-Gaussian, not
sub-Gaussian type of
sub-Gaussian, so not sub. Okay, thanks. Because then you get nice concentration inequalities, I suppose.
Yes, yeah, you are right.
Thanks a lot.
Thank you for your question.
Thank you very much, Enzo. So yeah, I will leave my question maybe for during the break, just to make sure that we respect the time. So let me stop the recording.